Now, a pendulum doesn't really swing completely freely, not in the real world. If we have a mass, let's just depict the mass as a sphere moving in some direction. So let's say we have a mass with a velocity in this direction, and this is a mass m. Then if the mass is moving, let's say, through air, there's some air resistance. And the faster the mass moves through the air, the greater the air resistance. Similarly, if the mass was moving through water or any other medium. So that we get a force of resistance, or a force that we'll call a drag force. And the drag force is opposite to the velocity. Drag force is in the direction that opposes the motion. It's going to be in the direction opposite that of the velocity. Now, drag forces can take many forms. One of the common forms for an object that isn't moving too fast in a medium that isn't too dense is drag force equals negative gamma times v, where gamma is a constant that depends on the medium and the nature of the pendulum, its size and shape. Okay, so a pendulum with a drag force experiences a net force equal to, first of all, the negative mg over L times x that comes from the tension in the pendulum string. Then it's times minus gamma times v. And these are all actually vector quantities. Now, v, the velocity of the pendulum, is just the first derivative with respect to time of the position. So that we can write this net force as minus mg over L times x minus gamma times x prime. We can write net force, of course, as mass times acceleration, which is mass times the second derivative of x, and that gives us a differential equation that we can solve for the motion of a pendulum